Hello guys, welcome to CSES group. Hope you are all doing well. Today we will be discussing 2017 questions from control system of UPSC CSE electrical engineering optional. Okay, this is the part 1. Part 2 is also there. So let's start with the question number 1A of 2017, which comes from the control system. And the question is, you are given with one open loop transfer function, which is here, and you need to find out the breakaway point, and also you need to specify whether the gain will be maximum or minimum in that point. Okay, so please understand, you need not to solve the complete root locus here, which is not required because you're only asking for the breakaway point. So this only we will identify, and the complete root locus will not plot. But before moving to that, we need to understand where the root locus lie in the real imaginary axis. So I am plotting here the poles and zeros of the given system. You are having two zeros, plus 3 and plus 5, and two poles, which is -1 and -2. Okay, so these two are two poles in the question, and these are the two zeros. Now when you plot it, or locate these points in the real imaginary axis, this is one zero that is at plus 5, this is the other zero at plus 3, and this is the pole, one of the pole at -1, and that's the other pole at -2. Okay, and let us now find out where the root locus will lie. So the thumb rule for identifying the existence of root locus in the real axis is, if you are at this point, you need to count the number of roots in the right hand side of this point. If that is the even count, then root locus will not lie in the right side. If it is an odd count, then the root locus will lie in the right side. So if you stand exactly at plus 5, the count is even. Okay, so no root locus, no RL in the right side of the plus 5. If you are standing here, if you count the roots, then it comes as to be 1. So it is odd, hence the root locus will lie. So root locus will lie from 5 onwards till this point. Similarly, if you are standing exactly at plus 3, still the count is odd, hence root locus will lie till plus 3. If you are standing here, let us say plus 1, then obviously the count is even, hence root locus cannot lie in this portion. Now, you need to recall which says that the open loop always, the root locus always terminates at, or ends at zeros. Okay, the root locus always terminates at zeros. So you can see I am writing the arrow direction or drawing the arrow directions ending towards the 0, and the root locus exists between -1 and -2, and the direction of arrow is different because root locus starts from the open loop poles. Okay, root locus starts from the open loop poles, and that's what I am drawing here, the arrow direction of or outside. Okay, it cannot go in this direction because there is no root locus which exists between 3 and -1. Similarly, -2 onwards till infinity, there will not be any root locus. Now breakaway point is the point, or break-in point is the point where the two root locus comes, or it goes or diverges from that point onwards. Okay, so the breakaway is here. As you can see, I'm writing here breakaway point because these two root locus will come together and they will go in certain direction like this. Okay, so that is why you are calling breakaway, it is going away. And break in because some root locus will come to this point, similarly some other root locus will come to this point, and they will terminate at this zeros. That is why this is called as break in point. And obviously you can see that if you have solved so many root locus question, you can easily understand this, the root locus for this question will come as a circular. But anyway, that is not required at this point. You are only interested in the breakaway and break-in point, hence you need to solve the dk by ds of this given open loop transfer function. So what you will do now, you need to write the characteristic equation, that is 1 plus gshs. So this is what the characteristic equation to you, and then you need to write down the k out of it. Okay, so I'm writing k here, just solve 1 upon gh, and you will find this equation, and then take this term in the right side. Okay, so that's what I am doing. So that is why it is coming in the numerator with a negative sign, and this s square minus 8s plus 15 will come in the denominator. Then you need to differentiate it once, dk by ds you have to do. So you have to do the dk by ds of this equation. You need to go for dk by ds of this equation, And if you solve this, you will get something like this. Okay, why you are getting this small equation? Because you are equating it to 0. So obviously the common parts and the denominator part will vanish, because this will go here, multiplied with 0 will end everything, and from here also the common part will vanish, and you will end up with 11s square minus 26s minus 61. And if you solve this small quadratic equation, you will find s is equal to 3.81 and minus 1.45. So obviously these 2 points are lying in the root locus. 3.81 will come here. Let me remove these annotations. Okay, so 3.81 is also lying between the root locus, and minus 1.45 is also there in the root locus. Okay, so this is minus 1.45 and that must be 3.81. Okay, nothing is as per the scale, so I am just writing or drawing it without scale. Hence you will not get exact distance here, but anyway you can understand very well. This is 3.81 and this is 1.45 with negative sign. Now whether the gain will be maximum or minimum, that you can only find by substituting this value in the equation. So that's what I am doing now. So you have two values, 3.81 and minus 1.45, and how you will identify whether it is minimum or maximum? So you have to go for mod of GSHS equals to 1. Okay, and then substitute it here. So I am doing so, I am writing s is equals to 3.81. I am solving first for this value. Equate that to 1, you will get the value of k. That's what they are asking. And k value for s is equals to 3.81 comes out to be 28.99. Okay, maybe you can call that as a 29. And when you substitute minus 1.45 in the equation, which is here, okay, just simply substitute s is equals to minus 1.45 and solve that equation and find out the k value. You will end up with 0.0086. Now you can finally write down this statement. For the breakaway point at s equals to minus 1.45, the gain k is 0.0086, which is minimum. And for the break-in point, please remember guys, the break-in and breakaway difference. Breakaway is associated with the poles and this is associated with the zeros. Okay, that is why in the question also they are looking for that. So you need to mention that break-in and breakaway very clearly. And the break-in point associated with the zeros at s equals to plus 3.8. The gain corresponding to that comes out to be 28.99, which is maximum. I have verified the values using MATLAB also, and I am getting exactly the same. This can be written as 29 also. So let us see the MATLAB result. Now look at here, this is what the root locus of the complete system given to you, and this point corresponds to the frequency 1.45. Obviously this is a negative frequency side, so don't worry, it will show in that way. So this is not the negative side of the S plane, hence the pole is written here minus 1.45, and the frequency corresponding to it is given as 1.45. Okay, so don't worry about that, it's the correct one. Pole is at minus 1.45 and gain corresponding to that is 0.0086, and that's what we got earlier. And the other value is 3.82 and the gain corresponding to it is 29. And look at here, that's what we wrote. This is at 5, this is 3, you can very well check. This is minus 1 and then minus 2 here, and these are the root locuses between these two and between these two. And finally they will get breakaway in this direction and move towards this value. The other one also move in this direction, and they will finally join or combine together, and they will terminate at these zeros. Okay, that's what the final root locus for this question. Moving to the next question. The next question is 4b. Consider the unity feedback having the transfer function as a divided by s square plus bs plus a. So this is what the transfer function given to you. You can call it as a CLTF. CLTF. This is the closed loop transfer function which is given to you. Okay, because they are writing C by R ratio. And determine the OLTF for the given, that is open loop transfer function, and steady state error coefficient. So C by R, the generalized expression is G upon 1 plus GH, and the GH is written as open loop transfer function. Okay, so GH is OLTF. So you need to find out OLTF. The first part of the question is you need to find out OLTF. So what you will do, you will take this S square plus BS common from numerator and denominator. If I take common, I will find this term. To this denominator of a, you will find s square plus bs, which I am writing here. And now it is in the standard format. You can very well see that g upon 1 plus gh is here. That means what? Gh can be identified as a divided by s into s plus p. Okay, so this is what open loop transfer function of your system. So this is the first part of the question which you have solved, and now they are asking for the steady state error coefficient. Please understand, this is a type 1 system. Okay, this is a type 1 system. Type is 1. For type 1 system, ESS for unit step is 0. Okay, and for unit RAM, it is a finite value. For unit RAM, it is a finite value. And that's what we will see. You can see now. I think this is not looking very good. I have written all these comments here also, so don't worry if you are not able to read this content. Now ESS can be written as limit s tends to 0, s into rs 1 upon 1 plus gshs. Okay, please guys, if you don't remember all these, you can comment in the comment section. I can take a complete lecture on the ESS identification for a system. Okay, all these are the numerical solutions, hence you please don't expect that I will in detail completely discuss all these small topics and the derivations. Okay, you will solve questions only when you are able to understand the concepts. If you are not able to understand, please give in the comment section such that I can take different lecture series or conduct a different lecture series for you for that one. So the static error coefficient, the positional error, basically when you are applying the unit step, is identified as this equation. Okay, this is 1 plus gshs. Some problem is there. Okay, there is a, so this is 1 plus gshs, and if you take this portion alone, then kp, that is the positional error coefficient, can be written as limit s tends to 0 gshs. Okay, so I am writing that gshs is a divided by s into s plus b. Substituting the limit, you will find kp is equals to infinity. Kp is infinity. ESS is identified as 1 upon 1 plus kp. Look at here, this equation gives the same thing, 1 upon 1 plus kp. Okay, that is the equation which you are getting from here. This 1 upon 1 plus kp. And kp is infinity. Obviously 1 plus infinite is infinite. Inverse of that is 0. And that's what I discussed, that ESS for type 1 system subjected to unit step is always 0. Okay, there is no steady state error. It will purely follow the unit step input which we will be providing here. That is why you are saying steady state error is 0. Now static velocity error coefficient, apply 1 upon s square, that is the unit ramp to the system. If you solve that in the same way, you will find that the ESS can be written as 1 upon kV, where kV is equals to limit s tends to 0 s into gshs. Okay, so gshs is here. This is your gshs, and if you substitute the limit like this, multiplying with the s, you will find that this s will get cancelled out. Okay, and you will end up with the a by b. Okay, that's what is there in the next slide. You will end up with a by b, and ESS is inverse of kV, so ESS is b by a. So this much error you will get, when you are applying the unit ramp input to the given type 1 system. Okay, there is always a finite error. It cannot follow exactly same as the input is moving. Now static acceleration error coefficient, it is given by ESS is equals to 1 upon k alpha or ka, which is equals to s square into gshs, where limit is s is moving towards 0. Okay, if you do so, you will find that s square you are multiplying, so obviously 1s will remain in the numerator. If that is the case, s tending towards 0, so everything move to 0. Inverse of that is infinity. Okay, so you'll get infinite error when you are using 1 upon s cube as the input to the type 1 system. Hence, this is not recommended. Now question number 5 is for gamma t is equals to 0.9 t, it is required that the steady state error should be less than 0.05. Determine the value of gain k and above of the above system. Okay, so you have a system which is here, and this RS must be 0.90. Okay, don't get confused. They are writing gamma t is equals to 0.98, but this is actually the input you are providing to the system. Now let us write down the GSHS of this system which is given to you. So obviously K and K block and 1 upon S into S plus 2 block are in cascade. Hence GSHS is K divided by S into S plus 2. And you can only identify the acceleration coefficient, velocity error coefficient, not the acceleration nor the positional, because positional error will be 0, which we have seen already in the previous question, and acceleration error is infinite. Okay, so you can even mention those two, but I am not mentioning here. You can only identify the velocity error coefficient in this case. So velocity error coefficient is S into GSHS, limit S tends to 0. This S will cancelled out, and you will end up with kV is equals to K by 2, and ESS is 2 by K. Okay, so ESS is 2 by K, and in the question it is given that the steady state error should be less than 0.05. Okay, so you just equate here 0.05, and you will end up with K must be 40. Then only you will get the steady state error as 0.05. Let us now move to the next part. Next question is question number 6b. The error signal shown in the given is shown as given to the controller. The initial controller input is 0. Draw the output of the controller if it is a proportional control with Kp is equals to 10, or if it is an integral control with Ki is equals to 2. Now please understand what is given to you in the question. You are provided with a signal which is provided to first to the proportional control, that is the part 1. The same signal is provided to the integral control, and you need to find out the output. Okay, so it's just multiplication of this input signal with the proportional control, this input signal with the integral control. That is the only question. They are just confusing us. So let us write the equation for this pulse. It is u of t minus 2 minus u of t minus 10 into 5, because its amplitude is 5. Okay, so this is what your signal, and now it is provided to the proportional error control. Its coefficient is 10. So what will happen, that ET will get multiplied with Kp, whose value is 10, and you will end up with 50. You will end up with 50 into ut minus 2 minus ut minus 10. If you plot it, you will find the same pulse just exaggerated with the acceleration or the amplitude, and you will find it is 50 is here, rest of the things are same. Now you are providing this to the integral control. So integral control is identified as Ki upon S. Okay, so this 1 upon S goes for the integration, and Ki is the coefficient of the integral control, which is given as 2. Hence you need to multiply with 2 upon S. Now please understand, we are writing this in the time domain, whereas I am writing the integral control in the Laplace domain. So either I should write everything in time and convolute that, or I can move to the Laplace and multiply that. Okay, please remember guys, time domain convolution is multiplication in the Laplace. So I am using the Laplace now. So I am converting this into the Laplace equivalent. Okay, so ut minus 2 can be written as 1 upon s e power minus 2s, and ut minus 10 can be written as 1 upon s e power minus 10s is multiplied with 2 by s, and you will end up with 1 upon s square e power minus 2s minus 1 upon s square e power minus 10s. Okay, so obviously 1 upon s square goes with the ramp function. So that's what I am writing here, 2 minus t minus 2 ut minus 2 t minus 10 ut minus 10. Here if you plot, this is a ramp which is moving in this way. Okay, and it will start from t is equals to 2, then from there you will get another ramp which will start from t is equals to 10, and it will go in this way. Okay, and its value, the amplitude is 10, the maximum value it will reach is as 10. Then question number 8a of 2017 is the continuous system as a transfer function is given here. Find the state model for the system. So I am using a very simple method for using the state diagram or drawing the state diagram. You are having 3 poles. One is at s equal to plus 2, the other at minus 3 and minus 4. Okay, so the simple rule is the number of degree or the poles gives the count of summer and integral. Okay, so you are having 3 poles, so 3 summers and 3 integral blocks are required. Okay, so 3 summer and 3 integral blocks are required. So I am using this cascade method. So this is one summer, that's the other summer, and this is the third summer. And these are the integral blocks, 3 integral blocks which I am writing. So let us realize the first term, 3 divided by s minus 2. So 3 is coming from the input which is here, and then s minus 2, so that is why you are having plus input, because this is a positive feedback, then only you will get denominator as a negative. Okay, please remember, for the positive feedback the transfer function can be written as 1 minus gh. Okay, that is why you are using positive feedback there. Similarly, you can write for the 1 upon s plus 3 and 1 upon s plus 4, and then the corresponding equations can be written as, this is x1, integral of that is x1 dot. Similarly, this is x2, integral of that is x2 dot. x3, integral of that is x3 dot. Okay, so if this is d by dt of x3, then that can be written as x3. This is d by dt of x2, then it is x2, and this is d by dt of x1, then this is x1. So look at here. Now look at the right side of this implementation, this block. x1 can be written as, or x dot can be written as, rather, x1 dot can be written as x2. Okay, this value, because this is the summer output, so I am looking for what are the inputs to the summer. So one is the x2, which I am writing here, and then minus 4 into x1. Okay, so these two terms are coming as the input to this summer. Now moving to this second summer, x2 dot is the output, so that's what I am writing here, x2 dot. One of the input is x3, so I am writing x3 here. The other input is minus 3 into x2. Okay, so this is x2 which is moving to this minus 3 and getting multiplied and added here. So minus 3 into x2 is coming this side. And then similarly x3 dot, which is the output of the last summer, and it is coming from the input u or r. So this is 3r, and x3 getting multiplied with 2 and added with the 3r. Okay, so this is 2x3. Now simply you need to write in the matrix form these two equations. So this is one of the matrix here, x1 dot, x2 dot, x3 dot, and then coefficient matrix A. These are the simple linear equation. I hope you can very well write these. And that's it for this 2017 for the first part. I'll be solving one question in the next part, which is from the Nyquist criteria. Thank you guys. Please comment and like and share, and also subscribe the channel such that you will not miss any videos for this one. Thank you. Jai Hind.